So I would also like to thank you, Luca, for accepting our invitation to give a talk at the CASS Talks seminars here. And I would also like to present Luca to our audience, right? So Luca received his master's and his PhD degrees in computer engineering from Politecnico di Torino in Italy in 2003 and 2007, respectively. He's currently an associate professor and deputy director of the DAWIN, or the Department of Computer Engineering in Politecnico di Torino. And his current research interests include reconfigurable computing, computer-aided design algorithms, fault tolerance architectures, and radiation effects and components and systems. He's the author of more than 180 papers, which is a lot, and he received several awards during his research activities. He's also an IEEE member. So, Luca, thank you again for accepting to do this talk here. I'm really glad to have you here. So, please.
Thank you, Jose. Thank you, Ricardo. Thank you for the invitation to give this talk. And I'm really glad here to give you a presentation about what is the current state of the art on design and mitigation methods for FPGAs in aerospace, especially commercial off-the-shelf FPGAs. So my talk today will investigate several aspects. I will give you first introduction about the context, so what is aerospace and electronics in aerospace with the considered radiation environment. Then I will go through the single event effects, especially upsets and transient on two major technology used for FPGAs. And then I will have a part of my presentation dedicated to tools for performing the analysis and mitigation, and also comparison with some study cases and conclusions. And that will conclude my talk. So I hope it will be interested for all the audience is currently looking at my presentation. So let's start with what is about the aerospace subsystem and the electronics on it. So basically, we have part of FPGAs that are used for the onboard computer and for the data handling system. And some of them are used for the vital part of, for example, for the satellite. Some of them are used for the onboard computer. And then we have a set of other resources that are adopted for the electronic subsystem. So I talk about memories, terminal units. In general, the payload for the data processing. This is typically related to the type of mission that it is adopted on. And then interfaces with the rest of the system. So where, let's say, connecting to sensors, for example, for the satellite, depending on the type of mission, again, that is used about. And clearly, the subsystem includes this part of electronics that is generally, let's say, based on CMOS technologies, for example. Then we have a part of the electronics for the satellite that are used for all the part of the sensor and the actuator. For example, I'm talking about star trackers or eventually complex sensors for monitoring the deep space, for instance. And all of them are characterized with different type of electronics and different type of peripheral that are used for this scope. On the other side, the payloads instead has a lot of instrumentation that is adopted. This is less vital with respect to the system in terms of the survival of the satellite, but of course it is extremely relevant too, because a good payload should work in order to have the mission that is finalized for the satellite. And these include instrumentation, connectors to LiDAR, radars, telecom interfaces, camera, etc., etc. And of course, we need also telecommunication system in order to have the control of the satellite operations with respect, of course, to the control that are provided from the ground base station. So if we talk about electronics in aerospace, we have to first of all, define the context of the radiation environment we are talking about. And we have to define the fact that radiation environment is a natural space. So we have a lot of particles, different type of particles. Some of them are, let's say, trapped by the Earth magnetic field. So in this case, they are in a given position in the atmosphere with respect to the position in the Earth. And some of the particles instead are related to what are defined as cosmic rays, so generated by the sun, or for example, they are coming from the outside solar system. And all these particles, basically, the main example it is to imagine electronics and everything actually involved by these range of particles of different types that traverse our electronics. And if we go to the specific case of these cosmic rays and with respect to the electronics, we can characterize the source of them. So, for example, a small percentage of them are avionics. As I will present you later, this means a different type of phenomena with respect to the other particles. Some other one are high energy protons, like the great percentage, so more than 85% actually. Then the remaining part are generally alpha particles that are, in some cases, secondary particles that are generated by the material used for the electronics, or for example, for the packaging and the structure of the satellite in this case. Of course, let's say satellite can have shielding to protect. Generally, this is something like aluminum shielding to reduce the impact of the particle. But some of the particles are with high energy and then traverse the shielding and then reach the electronics. So here we are talking about FPGA in particular. So on the whole subset of system for the satellite and for the aerospace in general, I'm going to talk on a small part, which is actually really relevant because it's used also for the flight computer, so from the vital part of the satellite, which are the programmable gate array. And today these devices are really well known, of course, and also really promising from the point of view of the commercial of the shelf, because their capacity and performance are actually comparable to ASICs, or even more in some cases. There are some techniques for mitigating them and to address specific particles. So it means that there are solutions. Today we will see some of them to analyze and to protect the circuits working on these devices with respect to the various level you want to adopt these techniques. And then there are some other characteristics for these devices that allow you to have a very interesting usage. I'm talking about the reconfiguration capability. It means that you can reconfigure this device where when you are preparing the satellite, so you don't have a fixed structure, but for example, before to launch the satellite, you have the time to adapt your design, and this is possible thanks to the fact that you can reconfigure the FPGA. For example, the flash FPGA has these characteristics. Or even reconfigurability should be observed in the, let's say, best scenario, that is the one where you can configure the device remotely. So basically, you can change the characteristic of your circuits from the Earth base station with respect to the satellite operation. This, of course, it's a relevant characteristics. There are some other characteristics for the FPGA in space. Well, these are not totally related to the technological aspect. I'm talking about, for example, the international traffic regulations. That, of course, is related to political aspects, and the cost of these devices. Some of these devices, especially the one that are radiation hardened, so with particular mitigated technology, they are, let's say, protected by these things. This is an important aspect with respect to the fact of using commercial off-the-shelf devices that typically does not go inside of this type of condition. So it's not ITAR protected, basically. So first of all, if we want to address the radiation in the FPGA, first of all, let's give a very quick overview about the technology. So we have mainly three types of technologies. The first one, it is anti-fuse. It is a one-time programmable technology, and this, let's say, is not exactly implemented dynamic configuration, but they can be used during the design phase. And then we have the static RAM and the flash-based one. Both of them are reconfigurable, but characterized by different type of cells. So In one case, we have the classical static RAM cell memory, which the characterization of our 6 transistor, classically placed in this scheme that you can see here for the static RAM memory. In the other case, in the case of the flash-based FPGA, here there is an example about the ProASIC FPGA. Instead, we have a floating gate that typically maintain the configuration memory. Instead, in static RAM, you have to reprogram it every time you will power on. The characteristic of these two devices is the fact that they can be reprogrammed. The scenario changed a little bit, as I will illustrate here later, but the technology also is strictly different, and the effects of the radiation on this type of technology change the type of result that you will have. So we have the technology that I will consider in all the part of the presentation. And aside of the technology, there is another aspect we need to introduce well, which is the architectures. What does it mean, architecture inside of an FPGA? What is an FPGA architecture actually? Well, it is a set of resources. I'm talking about lookup tables, memories, PLL, arithmetic units, and all the list you can see here. Very large list, of course, of resources. And the architecture of the FPGA, it means in which way we are going to locate these resources inside of the device. So what are these, the layout disposition of these resources? And because any type of this resource may change the characteristic and the functionality of the device. And as we will see later, the type of the lookup table or memory, for instance, that are used change also the phenomena that is, let's say, provoked by the radiation. So we need to take in account that type of resources will change the impact of radiation. Well, so we have to know the technology, the architectures, but then we need to understand better what are the radiation we are talking about. Well, this means to have another lecture, not these ones. And so I need just to give a quick overview about the phenomena that we need to consider. So we need we can simplify, let's say, in two different phenomena: the cumulative effects and the single event effects. Well, if we talk about cumulative effects, this means that we are referring to the long duration effects of the radiation. Typically, we are talking about total ionization dose or displacement damage. It means that the radiation is accumulated inside of the device. You don't have any suddenly change of the functionality of your circuits, but your circuit is going to progressively degrade in both the condition, in both total ionizing and displacement damage. This effect is somehow more related to the materials of the technology used. So typically, it does not create critical problems that are suddenly analyzed, but are necessary to be considered when you are doing, for example, deep space mission, where you need to consider years in space of the electronics, and so your devices should work for years. On the other side, instead, when we talk about single event effects, well, we have two important sub-phenomena to be considered. The critical one that should be investigated first when you use a technology in an aerospace device, it is the hard effect. So it means an effect that is going to permanently damage your circuit. In this type of effect, we have the latch-up, the burnout, and the gate rupture. That, of course, make a critics condition of your device because it's going to damage permanently your circuit. So you need to prevent it by means of specific device structure. And clearly, this, well, we need to analyze commercial off-the-shelf devices to see how much they are resilient, but not so much things can be done on the device point of view. Then the other effect that is extremely relevant is the soft error. Soft error is a category of phenomena that is subdivided in three major classes. The upset, typically referred to the modification of a cell, memory cell from 0 to 1 or 1 to 0. The transient, that means that we will have a spike inside of the signals that can propagate and eventually create problem later. Or a more higher level effect, which is the single event functional interrupt. This, of course, is induced. So the classification that I made here, it is at the same level, but actually the single event functional interrupt can be provoked by one of these two phenomena. It means that you classify an error when your application is going to have problems, let's say, in terms of transient phenomena. And this means that your functionality is going to be affected. Well, these effects can be generated by the particles. The particles are then considered here as proton and heavy ions. As I said before, most of the particles are of these two categories. So when we talk about electronics in general, FPGA now in space, we look on protons and heavy ions. There is an interaction of these particles with the material of the device. And we have also electrons to be considered, whether in the radiation, but mainly what we have it is to consider protons and heavy ions that will create a nuclear reaction inside of our device. What exactly is going to happen? It is that the particle is going to impact with different type of characteristics, let's say, because, for example, proton and neutrons can be classified as low, intermediate, and fast, depending on the speed and characteristics of the interaction of the particles. And well, here we are going to open a scenario that is also very large, but I will stop in this case because we are talking about type of nuclear reaction, type of elastic collision that we have, or inelastic one. All of these phenomena will be related to the type of material that are used in the cell. So needs a characterization that is important for FPGA, but is more related to the technology implementation that you have. As well of the photons that will affect the more, in this case, the TID scenario. And also in this case, we have several characteristics. All of these characteristics here reported are related to neutral particles. On the other side, instead, let's say, we need to understand that to classify the effect of the particles, and also to understand later if our design is working properly under a given condition, and what are the characteristics of our mitigation structure. There are some other definitions we need to consider that are used typically from the radiation specialists when they look on the usage of FPGA in space. So I'm talking about the flux, so the rate the particles are going to hit our device, basically. The fluence, which means how many particles we will have that impact the surface of our area of the device, and the total dose, which means, again, in general, how many radiation is absorbed by the device. Flux, fluence, and total dose are the three main units that are used to characterize the radiation, and then clearly to understand which is the sensitivity of our circuit of the FPGA, and which is the improvement we can obtain when we apply mitigation strategies. Okay, so the first one will affect the analysis property of the circuits, and the second one, the mitigation rules. The mechanism inside is different, but somehow we don't care so much when we adopt these techniques for FPGA, because the structure of the technology is fixed. We are not going to implement a new layout when we are talking about implementation on FPGA. But this can be eventually useful when we will look to the technology, to the realization of a new FPGA. Of course, photon will traverse and generate a couple of electron holes. Heavy ion generate a sort of group of electron holes that will affect the surrounding area. And instead, protons and neutrons are going to make a spallation effects, kicking, let's say, other particle inside of the material, creating a subsequent phenomena. The result of this that we are looking about kicking particles is, of course, measurable from the point of view of the dose, because you can, let's say, eventually observe with respect to the silicon area you implement how much it is the energy that progressively is accumulated, and sometimes you use some, let's say, parametric resources to optimize this. But on the other side, all the phenomena of the particles that I discussed actually will affect the type of signal propagation and characteristics that you have inside of your circuits. For example, if we think about a memory cell, a particle can change the threshold voltage shift. So it means that, for example, to change from 0 to 1, you will require maybe less voltage because the threshold will change. And this can change, of course, depending on the particle, but the point it is that you will address a different voltage threshold. On the other side, what you have, it is the characteristics or the mobility of the the particle and electrons inside of your gate structure, inside of the FPGA, will affect the speed of the signal, and eventually might change with respect to the characteristic of operational of your FPGA. For example, temperature and power condition. So all this scenario, as you see, is very, very large. And we can consider most of these phenomena connected to the change of the voltage characteristic inside the device. So this can be, as I said, the threshold of the voltage of the current, the possible generator of parasitic current, and then we have effect that can be related to the type of oxide that is used, so induced by the material that are generated here. The effect of the total minimizing dose. So if we want to look, what we need really to care, because we should go to the physics scenario, we need to more have an overview. Well, from the design point of view and from the architectural point of view, we need to have some simpler data to be analyzed. So one of these is the total ionization dose. In which way we are going to measure the total ionization dose? It is a parameter with respect to the kilowatts, so the accumulation of the radiation inside, and with respect of the thickness of the sample of the material. So you see that more it is the technology shrink, and more it is a TD that can be accumulated. On the other side, if we, let's say, look the phenomena, for example, of the transient effect that I said before, what we need to care, it is that when a particle crosses the silicon area of our transistor, it can crosses multiple levels, and then it can generate, let's say, glitches that can be upset or can be transient, depending on where we are going to have this phenomenon. If we go to the avionic effects, clearly this can be quite complex because we have the possibility that particle generate subparticles. So it's also difficult to individuate where exactly the particle is going to affect. So if, for example, we consider this square as our chip die, our silicon exposed area, where we are going to have the particle effect if we have the particle here. So any position can be true for having an effect, because not only the original particle is influencing the point where the ray is passing, but we have also these secondary particles that have high energy, so they can create strange phenomena. So it means that cannot be only, for example, single event upset, but if these particles are going to address in a given bit, might be on not only the singular cell, but the cell side are going to be affected. So the particle passes to this bit, but also this bit and this other bit are changed. And so we will have a multiple bit upset, or MBU, okay? So it is complex to analyze this scenario, and we will have a lot of definition to other definition to investigate that we will cut now, because what we need exactly to understand, it is an approximation of the model that we will investigate. A first approximation that is made for studying on the FPGA, it is the ion range. So you can mimic what is the probability density of a particle. So for example, here I make the hypothesis that the particle is, the ray of the particle is here in the center, and the energy is, let's say, decreasing following this distribution, okay? And this means to help the modeling of the particle propagation with respect to the position of the memory cell, for example. The other approximation that is made, it is with respect of the composition of the gates, of the technology. So you can have different type of technology inside of your device, but what we need to care exactly, it is the final effect. So we can make approximation of this individual different energy that is propagating in the various layers. Here the example show you that when the particle passes through several layers, this can be, for example, this is a floating gate implementation with different layers. As you can see, the energy, this is the energy released by the particle, is not the same, is not equal. So the final effect is the one we want to look, even if the radiation scenario is complex. So let's go to this point. In which way we define the final effect, which means upset or latch-up or transient. We need to look at the technology. Technology can be made with different way. We have different layers. A gate can be composed by different volumes of material inside of our architecture. So it's clear that if a particle passes through this, it can impact several layers here. So we need to identify where to address. But the point is that we can measure this. It can be measured by means of radiation test, and you will have actually a result in terms of cross-section. So it is somehow connected to the probability that your device is going to have a failure. This is measured with respect to the energy. So you need always to consider the energy. Why we need to refer to energy? Because the energy is related to the space environment we are going to use our FPGA. Is our satellite to be at low orbit or geostationary orbit, or let's say deep space? All these three different scenarios might change the type of energy where our particle will address our technology. So we have a different impact, and the resources here show you that you will have a different type of sensitivity for that, right? Good. We are going progressively to the FPGA. As you see, up to now, I really didn't talk about what is an FPGA yet. So let's go start with the VLSI cell. As I understand, at the moment, we are going to, let's say, make an approximation about the physical effect. We need to know the geometry. We need to know the traversed layer in order to understand which is, let's say, the type of phenomena we are going to generate. And here we are going close to the FPGA. When a phenomena is generated, clearly we can have a bit flip, 0 to 1 effect, as you can see here. Or eventually we can have a glitch. Here there is a, let's say, the transient phenomena, which is, as you can see, a change of the voltage status. Here I suppose I have my signal to 0, and then suddenly I have my signal that go and jump to 1. These two phenomena can happen in different positions in our technologies. To identify where this technology is sensitive to this radiation effect, and later to identify where on the FPGA we have this effect, we need some methodology. And here I spent some work about that. Methodology that can make an approximation of what we have on the circuit implemented on the FPGA and what we have instead from the radiation side can be obtained by means of a methodology that mimic the particles that are traversing the devices. Here I just show you that if you know the technology, what you can do is to load the model of the technology, so to have this description that is uploaded by a tool. The tool can eventually analyze what are the material and depth, so to have the structure of your gate, for example, and somehow it's generating, let's say, a three-dimensional structure of it, where you can later make the propagation of the particles. The propagation of the particle give you the energy inside of your gate. And what you can obtain for this propagation, of course, you have to modeling the physical effect. You have to mimic what are the particles doing in a real environment. So you need to use the energy and the distribution. But basically, the fact that you have it is that you have an array, a particle that propagate, that is actually array. This can be a straightforward line that eventually have the secondary phenomena here propagated around. And this generation can be connected to the layer, exactly in the picture that you can see here. Thanks to this result, what you obtain, it is that you can identify if some area of your gate are sensitive. So, for example, in this picture here, you can see, say, a heat map showing which parts are more sensitive, which parts are less sensitive, measured with a flip-flop, and then to identify exactly where this condition is critical. This, for example, this type of idea, you can find in this publication. It is applicable today to the flash FPGA technology and also to ASIC technology, because it's, of course, the technology based that can be adopted also on the ASIC side. Well, how you use all this knowledge from the physical aspect to investigate what we have on the FPGA. Let's say that the FPGA, as I said before at the beginning, we need the architecture, and the architecture can be summarized as a matrix of cell, as you can see here, with the input-output block, logic block, switch, where you have the routing. And the routing can be of different levels, so you can have long and short interconnections. The way your resources are implemented are the key about that. As I said before, layout is implementing your circuit functionality. So any lookup table, for example, is controlled by a configuration memory cell. The control logic inside of the FPGA, the flip-flop to implement the sequential element, everything is controlled by specific configuration memory cell, as well as the switching, the connection between the various cells. So everything has specific configuration memory cell. In which way they are connected to the layout? Well, first of all, we need to identify that the resources are can be modeled with a strict architectural connection. So a single effects can create a disturbance in the configuration memory, for example, or in the user memory. That in this case, it changed the data. For example, in this case, you have a data modification, a bit flip on the data. Instead, in the case of configuration memory, you can have a logic function, a lookup table that change from the version A to the version B with a given effect. And instead, with the routing, eventually you can have a wire, as I will see later, a segment that instead of being in a given position, after the radiation particle, this is open and you don't have any more the interconnection. Or as in the last scenario, we'll have a glitch, so a transient that is propagated. Okay, the connection between the layout and the characteristics of the FPGA, it's mandatory because you don't need to forget the geometry of the device. In particular, for the current state of the art RAM-based FPGA, mainly all of them is 2D technology, so it's a planar technology where you have configuration and logics. So as you can see here, you have the configuration cell that are interleaved by the resources. So from a logic point of view, your configuration actually it is a file. So say from the audience, if you know bit streams, clearly a bit stream is a file of bit, and everything is close together. They have specific organization, but you don't see if a frame, for example, of the bit stream is far from another one in terms of physical geometry. Instead, if you consider the layout, you will have this kind of scenario. So you have cells interleaved between them with logics. And this is actually what it is on the FPGA. It is important to identify this because in this case, if you know where the bits are with respect to the layout, and consider that you can achieve this type of information with several processes. I mean, if you go to perform some reverse engineering with laser, for example, you can identify which is the distance between the layers with respect to the other ones. And as you can see in this picture, it's not a very state-of-the-art devices, but to show you that configuration frames are interleaved, and the space that you are in the middle here, it is for the lookup table. So the layout is important to be considered because clearly a particle can kick a bit, but can also traverse a configuration logic. So you can have a multiple effect, not only a configuration memory bit upset, but also a transient that is propagated later. Good. What about the single event upset that we have in the FPGA? The modeling is really, let's say, present in literature. A lot of studies show them. So there is a configuration that has some interconnections. If we look at the interconnection, we have to consider that most of the interconnection, let's say 80% of the resources are related to routing. You can have multiple effects: opening, conflict, input antenna, output antenna, and also bridging. All these effects can be, of course, provoking an error in case the resource is effectively used, or eventually don't provoke anything because you will, for example, don't kick any kind of resources that is effectively used. So if we understand this point, we need to have a two comparison scenario. On one side, we have the FPGA configuration memory. On the other side, we have the circuit. The third scenario that we need to put inside, it is the execution time. So what happens when we have a radiation that is progressively kicking our device? Well, the radiation can affect the bit one by one, and this depends on the flux of the radiation. The flux in space might change depending on the solar activity, for instance. So it means that this particle can cross various bits. Maybe some of them doesn't address anything. For example, this point here is not kicking anything. But then suddenly what you have is an effect that is addressing a routing. And then you have the error. Okay? So during the execution, you don't see anything. until you don't have the bit that is modified, okay? Even if this bit might be accumulated in the configuration memory. In fact, one of the techniques that is widely known in FPGA and should be adopted when you use COTS FPGA in space, it is the scrubbing. The scrubbing means that periodically you will rewrite the configuration memory with a good bit stream, with a good information, in order to avoid that the SEUs are accumulated. This works because you don't accumulate bit, but does not protect you about the single event effect that we saw before, because whatever it is the correction that you gave in the previous scenario, you might have a particle that kick you the bit that is relevant for your circuit. And this is, of course, a critical point, because you need to take care of the scenario. You can compare that, scrubbing or without scrubbing. There are solutions for Aerospace even without scrubbing, because in this case you might have a very low flux and you don't need to care about that. But if you want to avoid that a single error will generate problem on your circuit, what you need to use is a classical technique that is called the TMR, or triple model redundancy. Thanks to these techniques, you will triplicate your circuits and you will be able to protect the scenario of your application, as we will see in the mitigation techniques later. We understand the single event upset phenomena that may happen in RAM cell or also in RAM memory on flash FPGA if we have module of RAM. The other phenomena that is relevant is the transient. The transient is a pulse. The transient is a pulse generated by the particles. So we understand before that we have a physical mechanism, basic radiation mechanism that generate these pulses here. The pulse might have different characteristics, can have a width, amplitude, can have different type of shape that propagate in the technology. Why it is relevant, transient, and where we are at the moment with the technology? Well, all of you and from the audience, maybe most of them know that the technology is going to shrink with very shrinked nodes. Not only, this is not only for space. And also the working frequency, this is related from RAM-based FPGA, it is increased. What is the problem from the error cross-section? Well, the error cross-section is typically increased because of the working frequency, because faster is your working frequency, the more are the particle you can, the transient particle that you can kick. But then here we have two other side phenomena. On one side, we have lower, smaller nodes. On the other side, we have a faster speed. And this contributes in two ways. The smaller node means that you can even have low charge particle to provoke an errors. On the other side, a faster working frequency means that you will sample more. So it means that the error cross-section for a given circuit is going to increase. This, of course, is valid for ASIC, but especially for FPGA, which is following a higher trend from the shrinking technology point of view. So what we need to do for analyzing this type of effects and mitigate it? We need to understand the source. The source, well, this is a spare model that it's a cartoon model that shows you that the particle can kick in various places, generating different type of pulses of different type of shape. As you see, amplitude is different, and propagated in different position. So once it is generated, we cannot make so much things. We need only to filter them. We need to find a way to understand how it propagates and in which way we are going to filter. Transient is a different story than single event upset because it is a pulse that propagates across the logic of our circuits. And basically, the scenario is very particulated because the pulses can change during the crossing of the nodes. It can start, for example, with a pulse like this, so very small and with a very short width. But then after a given propagation, it's really large, might be, because of the propagation of the gate. Or eventually, clearly, this shape is nullified. You don't have anything, because the pulses undergo to electrical effects propagation. If we consider this scenario, and I'm going to start from the root to connect to the type of application we will have later, the set phenomenon generation is, let's say, not possible to be addressed because we are not considered to mitigate by layout, but we need to understand where it propagates. If we understand where a transient propagates, we can understand which is the computational register it is affected by the transient. And in this case, we can identify that during the propagation, we will have a specific point that is addressed. Clearly, the transient can take different paths on our circuit. It can start here and going, as you can see here, in these different A and B, let's say, direction. In order to know that direction, we need to know the layout. The propagation might be different because we have different gate traversed, so the shape might be is not relevant for a given point, but becomes critical for another one. So in which way we are able to say that some glitches are filtered or some other glitches will be like propagated with a small delay, and so they are going close together and they create, let's say, a larger pulse. We need to analyze the way the circuit is implemented. And analyzing the way the circuit is implemented, we can identify that some glitches, for example, will be shrinking together and became a larger glitch. In this case, it becomes critical because clearly a larger glitch, sorry, if it is, let's say, similar to the shape of a signal, consider the higher frequency, this is going to be close, we will have to mitigate in different characteristics, and this became particularly critical. So the scenario is this one. We have a condition where basically the glitches are far away and can be filtered. The glitches are overlapped and they can be filtered. Or the glitches are, let's say, close together and they became a, let's say, a longer glitch. And this is a critical point because you will not be able to mitigate. The mitigation properties that you can see here, it is a structure where you have different gates, different filtering, and then this is fixed for a given shape of the transient that you will go to mitigate. So in this condition, you need to tune the characteristic of the transient in order to have the right mitigation. And where it is propagated, this transient? Well, it can propagate everywhere in our architecture. It can go in our long line structure. Here there is an interesting shape to see that the influence, this is the distance between the source point to the destination point. It became really critical if the distance is really high from the original point. This is due from the several characteristics of the devices we are going to analyze, because anytime we have an FPGA interconnection, you need buffering. The buffering will act on the type of transient that is going to be affected. And this transient can become critical if you are really far. We can use a lot of techniques to investigate that, because clearly now I give you a scenario of the phenomena, but you need to mitigate and to analyze them. So if you want to analyze, you can generate the pulses inside of the device. You can try to mimic the injection. This is not a realistic injection, sorry, a realistic transient generated by a particle, but you can program your circuits in order to create glitches. The way this is created, you can perform in the laboratory, because you can have a signal generator that creates a normal clock pulse. And then with this electrical injection tool, you can create this shape at the output that can affect the circuits. And you can measure in which way your circuit is sensitive or not to this transient. Clearly, you can do with a simplified architecture. If your architecture becomes complex, here there is a very, let's say, easy example, but just to show you. For example, here there is a chain of gates all connected in this type of serpentine placement. And this will change because the type of propagation can influence, can have influence due to the, let's say, the type of nodes traversed, the fan out, the type of divergence path and convergence. So if we look at these 4 different characteristics, which means in which way you have the layout of your circuit, which way is the topology, basically the pulses might change with different type of length and with different type of delay, and that's relevant. So if we want to exactly know in which way we can mitigate them, what you need to do it is to characterize. For example, characterizing the fan out is possible to identify that the fan out will be let's say, influencing the type of implementation we will have, and so we can tune the pulses. On the other side, the propagation is fundamental to understand which is the length, effectively length of the transient, because in this way we can be able to put a right filtering circuits in the input of the storage element, for example. Doing that, what we need to do, it is to automatize all this process. we spend this first part of the presentation talking about a lot about the physicality of the phenomena, the two major effects about the transient that we have on COTS FPGA, transient and SEU. And now we need to talk about how to mitigate and analyze them. And the only solution here it is to automatize, to make CAD tools to perform this automatization. Well, CAD tools, there are a lot of CAD tools. They can work on physical domains, structural domains, on the behavioral domains. And the point it is that in order to manage these effects, we need all these three scenarios. It's not possible to act only on the architecture, to act only on the behavioral, on the structural, because if you do the mitigation independently in these three phases, you will not be able to mitigate this effect. What we have is a scenario like this. Let me say that you design, you make the manufacturing, then you test, and then you can perform radiation test if you want to see if it is working. But you have different type of effect you can measure. For example, during the design, typically what you do it is to have timing, to have power. Today you can start to have some fault tolerance properties of your circuit. But when you perform a radiation test, or even later when you have your circuit that is used in space, for example, you will have phenomena like, as I said, ionization, or, as I said, single event effects. So the only way to protect your tool, to protect your circuit implemented on the FPGA, is to have a tool that takes this phenomena and put back in the design files. So to anticipate this information. In order to save money, of course, in order to perform a better analysis. Well, the analysis here does not has the aim to avoid a radiation test, for example. But with an analysis tool, what you can do it is to predict something, as well as you will do in the power. With the power, you have a power timing and timing analysis. You will estimate your performance of your circuit. When you will go on the hardware, you will see exactly what are the results. But you already have a prediction. And the only way here it is to have an expected TID scenario to be calculated by a tool, and an expected SEU rate. These are the two metrics you need to take in account. The CAD tool perspective, let me say, that is very, very large. So we can talk more than the time we are available now, of course. From the mitigation point of view, there are several techniques implemented from the layout point of view. Annular layout, ring gates, gang gates, redundancy, etc. That's not the point for FPGA. Again, for the FPGA, you already have something that is implemented strictly there. So I want to put inside the three different domains for the mitigation. Today, we are able to mitigate on the physical domain. You do radar the FPGA. That's not the case. I want to apply, to know the physical domain, but I don't want to apply mitigation on the layout. I want to apply in the structural domain, maybe by place and route, by placing different way the circuit. And I want to know which is the behavioral domain. So I want to have an analyzer that is able to let you know what is the application possibility to have an error given the radiation scenario. That's the solution. So if we are able to put together the application probability to have an error, given, of course, the radiation environment, if we are aware of the physical side of the phenomena and we know the structural implementation on the FPGA, well, we are able to do a good job for COTS mitigation, COTS FPGA mitigation in space, because we are able to understand effectively which is the dynamic scenario of the radiation that we will have on the FPGA. So the mitigation techniques here are, let's say, quite traditional. So what we need to do is, let's say, acting on layout, architecture, and design, okay? But what we will address here, it is architecture and design, as I said, because layout is a technique that is for, let's say, radar the FPGA or radar technology. So first of all, we need to consider that scrubbing is a must. So we need to apply scrubbing. The scrubbing can be performed in a different way. Eventually, you can have read back and scrubbing. So you read the configuration memory, and once you have an error, you configure. That is the scenario here. Or you can have a simplified architecture where you just wipe periodically the configuration memory. As I said before, you have this red position means that you don't accumulate errors, but you will have still errors there. So you need to protect with TMR, as I said. TMR is good because we'll avoid single event effects. It can be combined with partial reconfiguration of the FPGA today. And the way here, the state-of-the-art way that I summarized in this slide, it is that you need to make modular design of your circuits in order that when some modules of your circuit is subjected to errors, other circuit is working. For example, if you can see here, if I make the hypothesis that a TMR circuit is implemented in 3 different modules, module 1, 2, and 3 are equivalent, what you observe it is that when the module 3 is wrong, the other 2 are working properly. So it means that the full system here is okay, it's working fine because we have 2 out of 3 working. And here as well, we have an error, okay, but again, 2 out of 3 are working, so the full system is working properly. And you can correct properly. So the suggestion here it is to apply TMR, but with the partial configuration. And in this way, you are able to protect the implementation of your circuits. TMR is a widely known technique. I just report here the fact that the structure is with different type of scenario, because you can have 3 modules and you will have a voter. And this can be implemented in different way, with a single voter, with 3 voters, with different partitions. That's very, very large scenario. When you implement this on FPGA, you need to take care not only in the way you put the replica, but also the distance between the replica, in order to implement in a correct way also the mitigation of the transient, for example. Here there is a scheme to show you that if you put delay between replica, especially in the clock cycle management, what you will be able to do, it is to mitigate also the transient with the TMR implementation. Clearly here, the majority voter, as I said before, it can have different structure that can be adopted. Well, all of this can be applied to mitigate SEU in the configuration memory. Transient effects can be, let's say, include, for example, guard gate filtering. The guard gate filtering are implemented in some radar FPGA, and instead in COTS FPGA, you should implement manually, basically. So you need to implement it by means of VHDL or using place and route techniques in order to insert macro about the filtering. So it's not implemented automatically with the technology. Or eventually use some tools. So here I show you some academics tool that can be adopted for mitigating the device. One of these tools, it is, let's say, known in the radiation community. This is the single event transient analyzer tool that allows you to identify which is the impact of the transient in the circuits. And that's help you to identify what are the, let's say, the impact in the circuit's result. And here the framework includes the possibility to analyze the layout and the possibility to analyze the delay also. And that's include the possibility to identify exactly what are the flip-flops that are influenced by the particle. Here there is an example on how the propagation is performed. So basically each transient can affect one of these nodes, and the propagation might affect one of the cells, of course, randomically depending on the particle. If the particle affects this node here, it will propagate across this gate, from gate 1 to gate 4. We don't need so much what's going to happen when the propagation is performed during this step. So in this step here, it can change in several ways. If we are able to calculate, it's good because we can identify in which way the SCT will reach the flip-flop. So to understand if, for example, the transient will be sampled or not when it reaches the output flip-flop. This means that during the propagation, the transient will change. So you will have a source SCT with a given shape. Here it is an example, 0.35 nanosecond. And this you will, let's say, propagate up to 0.4. So during the propagation, it changes the result of your circuit. I think there is a question. I think well, I can directly answer now if the policy is correct. I see the question on the chat. The question, it is, let's say, also if you have double redundancy, the question is like this. You can always have the possibility of having 2 out of 3 circuits being affected by radiation. And the question it is, and this is all, you wouldn't know which one of them are the current one, because you have correctly, the question say, 1 circuit is wrong, you have 2 circuits working, you don't know which one is, say, correct at the end. The question is, would be better to have triple redundancy or better to have a shielding solution of the circuit? Well, the point about that question, it is that shielding is a solution, but you cannot shield all the particles. So there is no way to put a shielding that is protecting for all the particles on a satellite, for example. The shielding is a problem for 2 ways. I will maybe investigate also this at the end of the lecture. The shielding can be too much heavy for the satellite, okay? And that's need to be smaller. On the other side, you can have particles with an energy that are crossing the shielding as well. And so, let's say, this is not possible to be addressed, okay? So you need always to be to use redundancy. Redundancy can be adopted with triple model redundancy or even more. You can have NMR, so more model redundancy in order to protect them. I think I can give you some also feedback later to this phase. Just coming back to the propagation of the pulses here. The pulses, I will fast this phase because at the end it is just a propagation that is currently modifying in different way the let's say the shape at the output. So if you want to mitigate and analyze and mitigate that, what you need to do is to do a very complex modification of the original flow. Here there is the commercial design flow that is represented in this part. You have the VHDL, you synthesize, you perform the place and route, and then you have your circuit that is finally implemented. But if you want to mitigate, analyze and mitigate, what you need to do is to extract a lot of information from this phase. You cannot sometimes take the layout because these are proprietary information from the manufacturer. But what you can do is to extract the netlist, and if you do the characterization, to propagate the effects and to have the correct individuation of what are the flip-flops that are critical. In this example, there is an application of this SETA tool to the mitigated networks, that it is, let's say, a possibility to adopt these techniques. Mitigating, what does it mean exactly? It means to insert automatically in our commercial off-the-shelf FPGA a guard gate structure. The guard gate structure insertion, as I said, in commercial FPGA are mandatory because you don't have an automatic filtering. So what you need to do is to insert this structure in the middle of the logic. Here, there is just an overlap of the animation that does not show you exactly what is going to happen. But this green shape that is illustrated here, so the Q inverters and the other guard gate structure, should be included actually in this position here. Here you need to put the guard gate, or GG, how is it called? Because you need to filter not between the gates, but you need to filter at the input of the flip-flop. That's the mitigation works exactly here. There is a good picture to show you the fact that the pulses here traverse on the gate, it reaches this filtering, and then here it is nullified. And you don't have anymore the transient that will go to the pulses inside of the flip-flop. That is good because you need you can put this implementation. But then here we have a lot of things to be placed together. So let me try to make a wrap-up of the technology we are studying, and then let's go into some study cases that are interesting for the audience. If you want to analyze transient, we need to analyze the topology of the circuits to identify how it propagates the pulses and how you mitigate that in front of the flip-flop. If you want to understand the SEU effect, what you need to do is to understand the composition of the configuration memory and the circuits that is placed on. And you need some tool. Here is an example of what Polito made that investigate the configuration memory and identify the position of the bit with respect to the layout. In this case, we have both the condition. We have the possibility to identify the transient. We have the possibility to know where are the SEU affecting the configuration memory. What we need to add in order to make everything working, it is also to understand which is the impact on the architecture. Well, the impact on the architecture is another very big story, because first of all, FPGA designers know that we have a lot of tools to implement our second FPGA. Vivado and also VTIS from Xilinx are today tools that make an abstraction of the implementation in order to have a sequence that is implemented on the FPGA. But we want to obtain a classification and an error rate. Let's remind since the beginning that the result we want to obtain it is to understand how many errors we will see in our application. So in order to perform this operation, you need to make an encryption of the bitstream of your FPGA, and you need to identify what are the bitstream reference or the bit reference that are adopted in technology that allow you to identify what are the resources that are used effectively in your application. If you're able to identify these bits, what you're able to do it is to identify effectively what are the resources used. And this is an interesting point, because there are a lot of methods to automatically decrypt the technology of the FPGA, but most of these technology are very complex, and you need a lot of time to perform this encryption, like several years if you have this computational time performed. The point is to understand the memory and to identify the regularity, because if you understand the regularity, it's possible to identify the bits that are in common, and then to identify which is the effectively bit used for the decoding. And today, of course, here there is some example adopted with the Kintex 7 FPGA, for instance, but we have also coding applied, for example, to zinc technology that are effectively interesting to be adopted for aerospace. From the architectural point of view, what you need to do is to identify very interesting things. Here there is an example. There is an example about routings, two routings that are controlled by the same bit. This is a widely known phenomena in FPGA. You have these two segments, 4 bits of the configuration. Here, this number identify you the coordinates. And well, some of these bits, 2 in particular, well, 1 in particular is in common. So what's going to happen if a bit addresses this common bit? You have an error. And even if you implement TMR, as the question appeared before, you will not be able to mitigate them, because you will have an error that duplicates on 2 instead of that 1. And then you have the TMR condition that is going to fail and doesn't work anymore. So if you want to analyze FPGA from the point of view also of the TMR, you need to identify if there are this type of phenomena in order to avoid that you create this cross-domain failure inside of the architecture. And in that way, you will be able to protect the circuits, because you will be able to avoid 1 bit controlling more interconnection point inside of the FPGA. To do these things, of course, you need to CAD tools to control it, and the CAD tool here will be able to actually perform the analysis of the configuration memory. And that's the connection with the single event functional interrupter phenomena that I said at the beginning. At the beginning of the presentation, I was talking about SEU, this phenomenon of flipping the configuration memory of the user memory, transient that we understand. But how you identify if an application is going to have a SEFI, so the function that it doesn't work anymore? You need to put this information together in a single tool that allow you to accumulate the effects in the bit and connect this result to the application error probability. Thanks to this, what you will have, it is that you will be able to predict what is the error rate of your application, because you will know which is the upset rate of your technology in the space. This is given by the technology. So if you take a device, commercial one, you understand the technology, identify which is the upset rate, and you will be able to connect this to the application error probability of your circuits. This shape change depending on the type of circuit that is implemented. In which way this is changed is also really interesting, and I will not go so much in depth on this, but here there are 3 pictures showing you one circuit originally placed. This is a benchmark circuit in a plain condition here, so it is only limited in this area. Well, if you apply TMR techniques, some commercial TMR techniques, all the circuit start to be very big and fill the FPGA. But then if you apply some mitigation rules, again, it becomes a little bit smaller and theoretically also more robust, because you will not only play on the dimension, but you will play also on where lookup table and interconnection are made. Here I show you just some example of experiments performed to validate all of them, because at the end you need experiments to see if this scenario is valid. A typical experiment to show you to validate this condition, it is consisting of a controlling board, this is the zinc, and a DUT board, that is in this case a Virtex 5, quite old FPGA at the moment. These are irradiated. Irradiated means that you will have more than one bit flip affecting the FPGA in some moment. So you will need a process to manage all of them. The process will need to monitor continuously what is going to happen on the FPGA and to classify the error. If the error is classified, you need to store back the configuration to compare later, or eventually do a cleanup and then start again to perform the monitoring, because you want to monitoring under the bin. Well, the results you obtain are really interesting, because you can compare the various circuits I showed you before with respect to the error rate, so the application that makes error in the output. Here is interesting because you see the plane, the TMR. The TMR works fine only for a small number of bits, but once you have more bits without scrubbing inside the configuration memory, this is for SRAM FPGA, you will have an effect that is more critical because you have more resource used. But if you place correctly the resources, the blue line here, you will be able to reduce the error rate even in case of accumulated. So it means that you're able to extend the mitigation. And this can be performed in several ways, comparing the various circuits and showing you the various alternatives. This is another example. I forgot to put which is relation to, but this is a comparison about an ARM microprocessor implemented on some devices. So, starting to go toward the conclusions of the presentation, I want to give you some study cases that are interesting to be analyzed, that are related to state-of-the-art analysis we are doing. The first one is an ultra-energetic test. So commercial off-the-shelf devices, if they want to be adopted for deep space mission, need to be able to survive with respect to the ultra-energetic particles. So it means that there are particles that are possible to be generated on the ground in some, let's say, large accelerator facility, like this one has been performed in CERN. With 40 gigaelectron volt per particles, let's say. And if you apply this particle, you are able to start to study what are the phenomena in deep space. And here there is a comparison of these techniques. And if you compare all of them, well, first of all, you can use the tool I said you before to predict. But rather than, you can be able to observe on which it is the error rate with respect to the particle flux that you adopt. So with high energy particle. The good point here it is that the device, like this Kintex 7 family, this is commercial, survived to the radiation particle at ultra-line energy. If you apply TMR, you are able to improve the characteristic of your circuits, especially for small accumulation of upset. So if you apply scrub rate and TMR, you are sure to have a good protection. If you include even also TMR protection with some CAD-oriented tool, like the very place tool here is doing, you are able to perform and to have a good result, okay? Just to show you here, there is a comparison between the plain circuits and the TMR. Again, the interesting point of this shape, it is that position here, okay? The other result here is show you the cross-section. The cross-section is interesting because it's a measurement of the application error with respect of the circuit. As you can see, the configuration memory more or less is equivalent. This also is looking connected to the question made before. So you cannot shield, you cannot play with the technology sensitivity, because whatever it is the circuit you implement, the configuration memory will still upset in that way. But what you can do, it is to reduce the impact by doing this mitigation, okay? Because you apply thin air and you will reduce the impact of the application error. And depth analysis also allows you to identify all the other technology side phenomena. So, for example, given a position of the bit affected by a particle, you can identify all the cluster of resources that are interested. And this is really relevant because if you know the cluster, what you can do, it is to analyze this cluster with respect to the implemented circuit. Each of these clusters has a lower impact in the circuit. So the relevant one are the ones that are 2 bit flip or 3. But later on, you will decrease 2, 3, and 4. This is going to be negligible, but still happen in this space. So as you see, the commercial one are really relevant for this operation. But let's give you another example. Another interesting device that can be used for space in and using commercial are the Smart Fusion 2 for manufacturing for microchip or microsemi. Here the problem it is to analyze all the impact has been made from the particle in the cell, because the configuration memory basically it is without upset possibilities, actually SEU immune. The result it is that the particle will generate a pulse glitch that will propagate. This pulse glitch include clearly the phenomena of the drift effect of the particle, the contribution of the propagation, the diffusion, and then the propagation side. The interesting point here it is that the pulse is not equivalent. This shape is really strange, but provide you an illustration that is how the pulse propagate. The blue one is the original pulse crossing 14 lookup table, implementing inverters. In the illustration here, in order to don't have positive, so 0 to 0, 1, 0 and 1, 0, 1 pulses, I put only the odds transient. And as you can see, the original pulse is very modified, so it's enlarged up to the end, because the propagation changed during the traversing of the gate. If you're able to perform the modeling, as is illustrated here, you are able to control what are the results on the circuits. If you go inside of the technology, you can evaluate the difference sensitivity about the various basic resources implemented. Here you can observe the impact on multiplexer, on flip-flop, and on buffer. And this change depending, this is depending from the layout. You cannot play with this. This is due to the technology. And the only things you need to do it is to have the characterization and then to individuate or the CT propagate. The propagation can be classified in different way. You can classify small pulse, middle, or high, considering the shape and the amplitude of it, and also the propagation, so to evaluate the impact that can have these pulses on the circuits. All these things can be put together to individuate how much is sensitive your application. And well, this is interesting because you can put test circuits. Here I show you a comparison between different chains. They have thousands of flip-flop, and then they are interleaved by inverter gate. And the result that is illustrated here shows you that they have different sensitivity, clearly, and the possibility is to predict all this shape. What is the result illustrated in this point? It is that you have the pointer showing you the experimental result, and the line instead, it is the result of the modeling. As you can see, a good modeling can provide you a good prediction of what is going to happen on the real devices after the radiation. Last concept of my presentation is looking to the new technology, commercial technology for FPGA. Most of the FinFET technology and below the 24 nanometer technology are today implementing 3D technologies. So it means they use a techniques where you have 2 tiers of the technology put at a different level. The future generation of FPGA can have something like this. They can have the configuration memory and below the circuits. This is the geometrical disposition. So the effect here is much more different because you can have a particle crossing the configuration as well as crossing the resource of the lookup table. And what is the result of that? You need to know the layout in order to individuate this phenomena, but you can individuate the position where these are affecting, and then to individuate what are the nodes eventually affected by the particles. And in this case, the interesting point is that the scenario is depending not only about the size of the gate dimension, but also about the behavior of the circuit, because here there is an example showing the original gate and the mitigated one, where we put very large nodes. These both are very large because it means that you have a larger area of sensitivity. The particle crosses this point, and you have a static cross section that is higher. But thanks to the fact that you have a larger size of the nodes, the impact on your circuit, the impact of your circuit is lower, right? So if you look this scenario, the result it will impact specifically the performance and the size of the implementation of your circuit. There is a question reported here. I just commented now, and I can answer. Which are the main application domains, say beyond the aerospatial domain, that use these fault-tolerant techniques using COTS FPGA? There is a first application domains that is really interested to adopt these devices. That is the radiation facility, where you need to use specific sensor. Not in all the facility you can use, let's say, commercial devices for radiation facility because of the different level of radiation. But thanks to the performance, there are positions where you can adopt them, especially when the flux is not so intense. So you can adopt scrubbing with good frequency and TMR in order to protect them. So the main application domains after aerospatial domains are the one related to the radiation facility. There is a third one application, not only about after the radiation facility, that is automotive. Automotive is starting to use FPGA as well. Still, the costs are quite too much higher than the actual electronic control unit, but automotive start to be increasing, thinking to use FPGA, especially with the characteristic of their wide microprocessor. When you adopt these techniques on automotive, you will need to adopt techniques that are not normally using scrubbing, but you need to use redundancy. The level, of course, is different because here TMR specifically will need to be applied to the layout. So concluding from that presentation today that I made today, I gave you an overview about the mechanism to generate the phenomena inside of FPGA. These mechanisms are valid also for other technology, not only for FPGA, but also for ASICs. There are a set of traditional techniques for FPGA that I discussed. Basically, they rely on scrubbing, they rely on triple model redundancy, and on guard gate. These are the really three main scenarios. These three main scenarios then can have different alternatives. You can find on the literature a lot of examples with different alternatives of this implementation. I want to underline the fact that today there is a lot of interest in using COTS FPGA for cubes, and there are already missions that adopt these devices. Of course, some of them are still protected about, let's say, ongoing projects. So future years we will see this type of satellite implementing this type of devices. There is a need of a huge effort from industrial and radiation test experiments in order to support the tool development. Because the key point, as I hope you understand from this presentation, it is you have the phenomenon on one side, but on the other side you need tools to manage the analysis and the mitigation. So any type of support, any type of collaboration, also with respect to, for example, our institution in Torino that is studying this phenomena, is very welcome. So thank you for your attention. Thank you for the time you spent in my presentation. And I think even if we are a little bit late, I give the word to José to eventually manage some questions. Thank you.
Hi, Luca. Thank you for the great talk. First, I would like to address our viewers So if you would consider subscribing and turning on notifications on our YouTube channel, so that YouTube can let you know when we have new talks, when we go live, and also when we post-process the talks and they go live on YouTube. So Luca, thank you so much for your talk. I think you covered from the beginning, from the building blocks up to applications. So I think it was a really great talk. I have a few questions, but I'll mix them with questions from YouTube and from here. So first, Fernanda is here on MConf, and she's asking you, for 3D loop models and simulator, is it possible to perform in CMOS and FinFET?
So yeah, I answer this question to Fernanda. Yes, it's possible. The key point it is that you need to build the Z section of the device. So it's not only let's say the information that are available from libraries, for example. Typically, FinFET and CMOS have libraries that are describing the 2D characteristics, the layout of your circuits, basically on 2-dimensional. But what you need to have it is the depth of the material. This information can be extracted in different way. You can do in collaboration with manufacturer, or eventually it can be done by reverse engineering, or there are modeling. However, yes, it is possible to adopt these techniques 3D on CMOS and FinFET as well.
On that question, Luca, does the angle of the particle matters more in FinFET than CMOS, or?
The first result we had from FinFET, some FinFET models we developed, so not connected to a real device, showed that FinFET has points with smaller size that have more criticalities in terms of particles. And there are more nodes. So in principle, the analysis performed in with the different angular analysis showed this type of result. Let me say, Jose, that today we have literature results published, reviewed, and published with vertical analysis only at the moment. We are doing the analysis with the angular effects because we want to connect that with the tilting of the test, radiation test. So by means of tilting, it means that you will have your device vertically with respect to the beam source, right? What we want to do it is to tilt with some angle, and then to have the particle irradiating that way. In this way, we think we will generate possible particle crossing different in a different way the nodes, and we want to compare in that way. We are in the direction to do this operation. The answer to your interesting question, it is yes. The tilting will affect. It's already known that affect the depth of the device, but it will also affect the behavioral on the type of effect you will see. Like MBU will probably generate in a different way, or even transit will be generated in a different way.
Okay. Alexandre is asking a follow-up question on his first question on applications, and he's asking about certification procedures for automotive. Do automotive industry looks happy about FPGAs, or do they have some certification issues that we have to go through?
But this is a personal answer, by the way. Let's say that when they see this type of redundancy, they are not so much happy because the amount of redundancy is quite severe. So the idea there it is to have a reduction of the redundancy you want to apply. But the point it is that you need to follow specific certification process to allow this. For sure, there was a previous presentation in the CASS here, especially I think from Fernanda last week's, about the fact that you can have neural network, for example, so different type of complexity to manage this. You need to have certification. And when you talk about this type of technology, let's say the one related to the talk today, that we can say that for space are really traditional and they are consolidated. They are not the same for automotive. So you will not have the same. They are also with different standards, right? because you can have the DO254 for aerospace, but then there is the EC standard for automotive that includes different way. So there is a difference. There is a gap actually also. The gap is a little bit smaller when you talk about memories, but when we talk about the circuits, that's huge. But they start to evaluate, especially eFPGA. So when you have the FPGA inside of the device in general.
Okay, thank you. Okay. I also have a question. This is my question, actually. You talk a lot about FPGAs, and I think one of the main reasons why we like FPGAs is reconfigurability, right? Especially partial dynamic reconfiguration. On your PIP analysis, can you consider partial reconfiguration? Or
yes.
It takes longer?
It's possible to consider partial reconfiguration. It is difficult to perform an analysis validated by radiation test. One thing that I had in mind before to give this talk was to provide test in any of the, let's say, observation I gave you. So any type of things has been with some test connected to. So when we do partial configuration, we only did some radiation test campaign, and we don't have a full comparison about that. The tool are managed this, but there are still some effects that are not possible to be managed, especially because configurable regions require controllers. Controllers is also exposed to radiation. So once you need to validate these techniques, you need to take in account this scenario, and sometimes this is difficult. We have some preliminary works also in literature, but some works need to be done. Yeah, manageable, but still room for improvement to characterize effectively. Let's say that if I need to say, is this techniques applicable already to industrial design? Not yet. We need to perform some further tests to be sure to do this.
We have another question from Paraná, from Volney. He's asking you, have you modeled any applications using safe state machine feature? Have you tested them under radiation?
Yes. The result, I try to catch the slide about the result. Some result about the radiation test illustrated in here, for example, are related to microprocessors and counters and circuit with finite state machine inside. Let's say that we put already microprocessor. We didn't do a specific test when we put some finite state machine design in the dock for this. Just to give a link to the question you gave me, it would be interesting for finite state machine to evaluate the clock domains and, for example, the clock resources inside the FPGA, because you can adopt clock divider, you can and also multiply. You can have PLL, increase the clock frequency. It will be interesting with finite state machine to use this type of counters or finite state machine to evaluate the impact on the clock.
I have another question. That's for myself also.
Okay.
Comparing for aerospace and avionics and self-driving cars and stuff, when is it better to use FPGAs or ASICs? I mean, from a financial point, this is quite clear, right? You need a lot of consumers to do an ASIC, but you can use FPGAs and prototype something in a minute, right? But that aside, when are you looking into using ASIC or FPGAs?
Okay.
How good is partial reconfiguration? That would be my question.
Mm-hmm. Yeah, in fact, I was thinking exactly to this question when, let's say, to the reconfiguration characteristics. And that's the experience, for example, I have. That, first of all, for aerospace application, in my experience, the reconfiguration in the term of performances has not been yet the target of the flight computer, for example. In aerospace, let's consider, for example, the COTS for CubeSat. The point it is that you have a circuit that you can manipulate up to the launch of the mission, let's say, or to the long phase. So you have to think that when you prepare a mission for a satellite, here I didn't talk, but we had an experience with the Euclid mission that still need to be launched. There is a project that is starting, let's say, several years before the launch. So what will be the evolution of the design during these phases? You will go stuck with an ASIC, or you prefer to have an FPGA that you fix, you debug, or eventually, if from the mission point of view, you need some feedback and then you update your circuit. And in that case, for example, in the Euclid mission that used the weather radar in that case, because it was a type of mission you requiring this type of satellite, it was not a CubeSat, let's say. The good point was to use a 5-programmable get array with Flash, because in the 4 years of development, a lot of things changed from the requirements. And so the reprogrammability there, it was during the design phase, not after that. Then the other point is, again, I talk from my experience, automotive is starting to look, but not yet ready from the cost point of view. Some functionality are really timing driven inside of automotive, and some ASIC are really already designed well for that. The point is that there is a transition ongoing with different fuel source, with the autonomous driving, but also from the power sides. Okay, so the power training, well, probably will go to be electric. So some controller will disappear from what we have now that are standardized for ASIC, and that will be maybe the change. The evaluation today is more on the eFPGA because they find a possible optimization of what we had before, and that's the context, right? But however, let's say as an FPGA designer, as you, let's say reconfigurability is not yet the target, and this is, let's say, things where researchers should work on to make the idea of having reconfigurability really the case for a given result. Reconfigurability today is valid for server. So if you look in the networking side, servers are adopting reconfiguration. And so they use it, for example, for dynamically switching the signal inside. But for avionics and aerospace and automotive, we have this still this skeptic use of reconfiguration.
So basically what you're saying is that hardware designers for avionics, they want to finish their job the day before the launch.
I didn't want to exactly say that, but it is a specification problem, that one.
Yeah, but if you look at software developers, they want to finish the design after the launch. So
yes.
We're still okay.
That will be the case for our configurability, actually, yeah, because you will need to correct later. That's really good.
Yes, upgrades, add-ons. Luca, I have one final question, also from Alexandre, and he's asking, in terms of architectural mitigation methods, besides TMR, and he mentions guard gates, and I believe he's also mentioning duplication with comparison, or DMR. Besides that, what can be used in FPGAs?
You can use DMR also. The issue there, it is that it's really difficult to have the certification with the DMR. Also for mission for CubeSat. So during a project of CubeSat, even academic project, so that will be, let's say, very research orientative, you can test DMR, but if you need to do some vital component, it's really difficult to say you will not use DMR. Even if probably there is the possibility, because we are all aware that we do very pessimistic calculation for the for the error rate point of view. So the personal opinion it is that you can use DMR, but it's really difficult to claim that you can survive with some vital resources. So you can have in your payload, but not a vital part of your satellite. So let me say it is a research point, but not possible to go in another point. Let's say TMR is mandatory, and guard gate also. Guard gate, you need to think that TMR and guard gate in radar the FPGA are fixed inside, right? So they are already there, implemented automatically in some FPGA. So it's layout oriented with TMR. So when you use COTS, you need to implement by your design, and you need to use them. Again, you cannot use guard gate, but when you do the certification, you will incur in more error rate. So difficult, really difficult to not go in this direction. So it's more research. It's research work actually there again.
I actually have one final question, but this is the last one. Which are the open challenges that you see in aerospace and overall, and to ship a satellite into space? For example, we haven't shipped yet a GPU into space, for example. So do you see, and also, but we are already embedding GPUs on self-driving cars. So can you see some open challenges that we have to face in the short run and in the long run for aerospace and also for Earth applications like self-driving cars and so on?
Yeah, so let's say it's clear that also aerospace domain is really sensitive to the type of performances you will gain if you implement, for example, neural networks on FPGA. So the point I see, say, two main challenges there. One point, it is from the application point of view. So the possibility to have a neural network, it will be very interesting. It will fast enough. Some application, I give you an example, algorithm used for landers, for recognizing where to land, will be sometimes faster if you have a trained neural network that elaborate images with respect to traditional architectures. But we are really far from having, let's say, a good characterization of this technology, because as you clearly know, we are still under investigation even for ground application to see how much are good or not for this type of scenario. But this is an open challenge, because it's clear that if for image elaboration, like a lander, will be faster. So it's in an open challenge. The second point, however, it is, let's say this is more from the personal orientation of this work, it is the technology one. The trend now, it is this one. We have the FPGA that before was fully programmable. So totally a mesh of array. Then they identify that you have to use a static part, then a reconfigurable part and communication. Then the evolution continues to say, okay, the static part, why we need that programmable? We put hardwired. So if we are talking about a state-of-the-art today FPGA, we are talking about a microprocessor that is hardwired, or even more processor hardwired, and then the configurable parts. So the point here it is that how to manage to characterize these devices under radiations and in the usage of aerospace. And if you join these two, as let's say some of our speaker today and in the last CASS Society days, we know, we are talking about a neural network implementing this system where you have microprocessor and part of the logic. So the challenge there, it is how you to identify if an effect is dangerous on the microprocessor or in the reconfigurable area. So that's require a lot of tests, and they require a lot of possible alternatives. Considering that in that scenario, TMR might be not the best solution, because neural network can implement triple model redundancy intrinsically inside, right? So that's a challenge also. So I see these two scenarios, mainly the fact it is the FPGA has this processor hardwired and programmable logic, right?
Perfect. So that was my last question. So thank you again so much, Luca, for your